Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to travel beyond the planets, beyond the broad disk of icy worlds, past Neptune, and toward a place no telescope has ever photographed as a complete cloud. It is called the Oort Cloud, although it is not a cloud in the ordinary sense. There are no rolling banks of vapour, no silver mist, and no convenient boundary waiting beneath the sign that says the solar system ends here. Instead, astronomers infer an immense sparse population of frozen bodies from the rare comets that fall inward from very distant orbits. The picture is familiar, a pale shell surrounding the sun. The evidence is subtler. We see the visitors measure their motion and work backward toward a home hidden in darkness. So tonight's question is not only what may be hiding inside the Oort Cloud, it is also how science can know that an invisible place is there at all. From the room around you, the solar system may feel comfortably arranged. Earth travels around the sun. Beyond us move Mars, Jupiter, Saturn, Uranus, and Neptune. Farther out lies the Kuiper Belt, where Pluto and many smaller icy bodies follow the same broad planetary plane. Diagrams usually fit all of this onto one neat page, which is kind of the universe, because the universe has never shown much interest in fitting onto stationery. The Oort Cloud belongs to a scale that makes even the outer planets seem close to home. Yet we do not need to begin with its largest distances or its most uncertain estimates. We can begin with something much smaller, a dark comet nucleus perhaps only a few kilometers across entering the region, where sunlight can finally warm its surface. Gas and dust begin to stream away. A faint coma appears, a tail develops. For a brief time, an object that may have spent ages in deep cold becomes visible from the inner solar system, carrying evidence from a place we cannot directly inspect. Before we drift any farther, I'd love to know where in the world you're listening from tonight, and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you liked the video and subscribed to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. If you could examine one pristine Oort Cloud comet up close, what would you most want to discover inside it? Perhaps you would look for unusual ice-complex chemistry, a record of where it formed, or some clue that its history began in a part of the young solar system very different from the place where it travels now. There is no wrong answer. These small objects invite large questions, which is a rather efficient arrangement for something that spends most of its existence almost completely unnoticed. Now let your shoulders settle, allow the room to become a little quieter, and let the details pass without any need to hold on to them. There is no test waiting at the end of this journey. If a number slips away, the story will continue. If you fall asleep somewhere beyond Neptune, the comet will not be offended. We can move slowly and ask only the questions that guide us forward. Where do the familiar regions of the solar system give way to this distant reservoir? Why do some comets arrive from directions far above or below the planetary plane? How can an orbit reveal a journey lasting thousands, millions, or perhaps even longer spans of years? What forces placed icy bodies so far from the sun? How can the Milky Way disturb objects that still belong to our own star? And when astronomers draw a spherical cloud around the solar system, how much of that image comes from observation, how much from calculation, and how much remains an educated reconstruction? Our scientific starting point is not the cloud itself, it is motion. When a comet enters the inner solar system, astronomers observe its position against the background stars over many nights. Each measurement helps determine its direction and speed. Gravity then provides the rules connecting those observations into an orbit. Some comets return relatively often on paths strongly shaped by the planets. Others follow extremely elongated routes and may not come back for many thousands of years. A few have calculated periods stretching much longer. Their incoming paths can also be steeply tilted compared with the orderly plane in which most planets travel. This wide spread of directions matters. A flat source like the Kuiper Belt naturally sends many objects along orbits still related to that plane, but long-period comets arrive from many parts of the sky. Taken together, their motions suggest a much more extended and nearly spherical source surrounding the planetary system. Not a photographed shell, a pattern written in trajectories. This is why the Oort Cloud is best approached as a scientific reconstruction. Astronomers do not point a telescope toward one dark patch and see the whole reservoir glowing faintly in the distance. Its proposed objects are too small, too dark, too cold, too far away, and spread through too much space for that simple view. Most would reflect very little sunlight toward us. Even if the cloud contains an enormous number of bodies, the distances between neighbouring objects would be vast. It would be less like flying through a snowstorm and more like crossing an ocean so large that each drifting grain of ice has an ocean of darkness around it. The analogy is imperfect because these bodies follow orbits rather than floating freely, but the emptiness is important. The Oort Cloud may contain a great multitude without appearing crowded anywhere. To move deeper into the mystery, we must now choose one faint visitor, measure the curve of its path, and follow that path backward beyond the region where sunlight gives the comet a tail. A long-period comet arrives like a traveller whose road extends far beyond the map. By the time we notice it, the journey has already been underway for an enormous span of time, and the object itself may still be little more than a dark point moving against the stars. It has no glowing tail while it remains far from the sun. That familiar silver trail appears only later when sunlight begins warming the surface and releasing gas and dust. Before that transformation, the comet is simply a small nucleus following gravity through the darkness. Astronomers begin by recording where it appears from night to night. One observation gives a position. Several observations reveal a direction. More observations show whether its apparent motion is speeding up, slowing down, or curving. From these measurements, researchers calculate the orbit that best matches the comet's path. It is rather like seeing a boat enter a harbour, and using its speed and angle to estimate the route it followed across the sea, except the sea is three-dimensional. The harbour is moving around the sun, and the boat may not return for many thousands of years. The path of a comet is described by more than one number. Its orbit has a shape and orientation, and a closest approach to the sun. It can be tilted relative to the plane of the planets, and that tilt may point in almost any direction. It can pass near the sun or remain safely beyond Earth's orbit. Its trajectory may be tightly bound, loosely bound, or so close to escape that a small gravitational encounter can change its future completely. Many long-period comets travel along extremely stretched ellipses. Near the sun they move quickly. Far away they slow until most of the orbit is spent in darkness, where the sun becomes only a brilliant star among many. This uneven pace is important. A comet may rush through the bright inner region during the brief part of its life that we can observe, then spend nearly all the remaining time far beyond the planets. The glowing visitor is therefore not the comet's normal appearance. It is a temporary performance caused by warmth. Most of its existence is quieter. To follow the comet home, astronomers try to reconstruct its motion before it entered the region, dominated by strong encounters with the planets. Jupiter is especially influential. A comet passing near that enormous world can gain orbital energy, lose it, change direction, or be thrown onto a path that leaves the solar system entirely. Saturn and the other giant planets can also alter incoming trajectories. Even without a very close encounter, their combined gravity can introduce small changes that become important when the orbit extends across immense distances. The comet itself may complicate matters as well. Jets of gas escaping from its sunlit surface act like tiny thrusters, producing forces that gravity alone does not predict. These pushes are weak, but orbital reconstruction is a patient science, and weak forces have a habit of becoming noticeable when given enough time. Astronomers therefore distinguish between the orbit observed near the Sun and an estimated original orbit calculated before recent planetary disturbances and outgassing changed the comet's motion. When many original orbits are considered together, a pattern begins to emerge. The arriving comets do not all approach from the same narrow band of sky. Their orbital planes can be steeply inclined, and some even travel around the Sun in the direction opposite to the planets. That broad distribution is one of the strongest clues behind the idea of a distant, roughly spherical reservoir. A source shaped like a flat disk would tend to preserve a stronger preference for the planetary plane. A spherical population can send objects inward from above, below, and every direction between. This does not mean each incoming comet points neatly back to one fixed location, as though the Oort Cloud were a village with a return address. The outer solar system is dynamic. Galactic gravity, passing stars, planetary encounters, and the accumulated uncertainty of measurement all influence the route. What matters is the collective pattern. One orbit may be ambiguous. Thousands of observed comet paths become a population of clues. There is another subtlety. A comet approaching the Sun for what may be its first passage through the inner planetary region can behave differently from one that has returned before. Repeated solar heating can remove easily vaporized material, reshape the surface, open new vents, close old ones, and sometimes fragment the nucleus. A comet that appears unusually active is not automatically pristine, and a quiet comet is not necessarily ancient in some special way. Its behavior depends on composition, size, rotation, surface structure, and previous history. Astronomers use the term dynamically new for comets, whose reconstructed orbits suggest that they have not recently passed close to the Sun, but even this label describes orbital history rather than guaranteeing untouched material. The comet may have experienced radiation collisions and internal changes during its long residence far away. The hidden reservoir is an archive, but archives can gather, dust, lose pages, and occasionally misfile an entire chapter. Still, these rare visitors offer our most direct connection to the distant cloud. We can study the gases released from their nuclei, measure the dust they scatter into space track, how their brightness changes, and refine their trajectories as new observations arrive. Each comet provides only one small sample. It cannot reveal the total population, the largest hidden members, or the exact shape of the reservoir. Yet the orbit carries a quiet message. It tells us that the object came from far beyond the familiar planetary zone, from a region where its motion was only weakly tied to the Sun, and where outside gravitational forces could gradually redirect it inward. Following that message backward, our imagined journey now passes beyond Neptune and approaches the broad disk of icy bodies commonly called the Kuiper Belt. It may seem that we have nearly reached the comet's home, but the Kuiper Belt and the Oort Cloud are not simply near and far versions of the same place. Their shapes, their orbits, and their histories lead us into two very different regions of the solar system. Beyond Neptune, the solar system does not immediately become the Oort Cloud. First comes a broad, cold region, where thousands of known objects still move in a pattern that remembers the planets. This is the Kuiper Belt, a flattened population of icy bodies extending outward beyond Neptune's orbit. Pluto belongs here along with many smaller worlds, whose surfaces preserve frozen methane, nitrogen, water ice, and darker compounds altered by radiation. From a distance, the Kuiper Belt may look like the beginning of the solar system's remote wilderness, but it remains comparatively close, compact, and orderly. Its members travel mainly within a thickened version of the planetary plane, the same general disk inherited from the material that formed the Sun and planets. Their orbits can be tilted and stretched, sometimes dramatically, yet the population still carries the shape of a disk. The Oort Cloud, by contrast, is thought to spread around the Sun in nearly every direction. Reaching it means leaving not only the planets behind, but also the familiar geometry in which most of the solar system was built. The distinction begins with how these objects move. Many Kuiper Belt bodies occupy stable orbits controlled by long-term gravitational relationships with Neptune. Pluto, for example, repeatedly completes 2 journeys around the Sun during the time Neptune completes 3 a resonance that prevents close encounters despite their crossing orbital distances. Other objects follow less protected paths and may be slowly scattered by Neptune's gravity. They form part of what astronomers call the scattered disk, a population with elongated, often inclined orbits that can carry objects far beyond the main Kuiper Belt. This scattered region is not a thin ring with a tidy outer edge. It is more like a broad spray left by the early migration of the giant planets, containing bodies whose paths have been stretched but not entirely detached from Neptune's influence. The terminology can seem more organized than the reality. Nature rarely arranges its outer districts according to the labels in our diagrams. Still, the labels help us follow a gradual change from a flattened planet-shaped system toward a far more distant and weakly bound population. Farther out, astronomers find a smaller group of objects whose orbits remain well beyond Neptune even at their closest approach to the Sun. These are often called detached objects because the known planets cannot easily disturb them during their present journeys. Sedna is one of the most famous examples. Its orbit carries it from a region beyond the main Kuiper Belt to an extraordinarily distant turning point, yet even Sedna does not provide a simple sign announcing the entrance to the Oort Cloud. Some researchers regard such objects as possible members of an inner Oort Cloud. Others place them in a transitional or detached population whose origin may involve early stellar encounters, the migration of the giant planets, or an unseen gravitational influence in the distant solar system. The evidence remains incomplete because only a small number of such bodies are known, and discovering them is difficult. They spend most of their time far from the Sun, moving slowly and reflecting very little light. We tend to find them near the closest part of their orbit, which means our sample is shaped by where our telescopes are capable of seeing. This creates a wide and uncertain middle ground. The Kuiper Belt is observed directly through reflected sunlight. Its objects are faint, but many have been photographed repeatedly, and their orbits can be followed across years. The outer Oort Cloud is inferred mainly from long-period comets that arrive from vastly greater distances. Between these populations may lie the inner Oort Cloud, sometimes described as a more compact reservoir of bodies whose orbits are distant enough to avoid the planets, but still more tightly bound to the Sun than the outer cloud. It may be flatter than the distant spherical population, or it may contain several overlapping structures produced during the solar system's early history. We do not yet know. The transition is therefore not a border, but a change in orbital behavior. As we move outward, Neptune's direct influence weakens. The remembered plane of the planets becomes less dominant. Encounters with passing stars and the broader gravitational field of the Milky Way become increasingly important. The solar system gradually stops behaving like an isolated planetary clockwork and begins responding more clearly to the galaxy around it. The difference between the Kuiper Belt and the Oort Cloud also tells a story about origin. Kuiper Belt objects appear to have formed in the outer regions of the young planetary disk, although many were shifted from their original locations as Neptune and the other giant planets migrated. Oort Cloud objects may have begun much closer to the forming giant planets. Repeated gravitational encounters could have thrown them onto enormous orbits, while the gravity of nearby stars in the galaxy altered those orbits enough to keep some bodies from simply returning. Two objects made from similar mixtures of ice and rock could therefore end up in very different populations. One might remain in a broad disk beyond Neptune. Another might be sent thousands of times farther away following a path tilted almost randomly compared with the planets. Composition alone may not reveal which region an object belongs to. Its orbit is the more useful address. Even then, the address is written in pencil because gravitational interactions can move objects between dynamical categories over the age of the solar system. So where does the Kuiper Belt end and the Oort Cloud begin? There is no universally visible dividing surface. Instead, astronomers look for changes in distance, orbital shape orientation, and the forces controlling an object's motion. Near Neptune, the planet's gravity remains a central influence. In the scattered disk, that influence stretches outward along highly elongated orbits. Among detached objects, the connection becomes less obvious, and the possible history more uncertain. In the proposed inner Oort cloud, external forces may have helped lift objects away from the planetary region. Farther still in the outer cloud, the orbits may be distributed throughout a vast spherical volume. Each population fades into the next through a landscape shaped by motion rather than solid boundaries. We have now moved beyond the familiar icy disk, but the distances ahead are so large that the Kuiper Belt will soon seem almost like part of the inner solar system. The next step is to ask how large the Oort cloud may truly be, and why every attempt to draw its outer edge produces a slightly different map. The Oort cloud is too large to fit comfortably inside the ordinary map of the solar system. On a diagram where Earth, Jupiter and Neptune remain visible together, the proposed cloud would either disappear beyond the page or force the planets into a tiny knot around the Sun. Even the Kuiper Belt, which already feels distant, occupies only the innermost portion of this larger scale. Estimates often place the beginning of the inner Oort cloud thousands of astronomical units from the Sun, while the outer population may extend through tens of thousands of astronomical units, and perhaps farther. 1 astronomical unit is the average distance between Earth and the Sun. Neptune travels at about 30 of them. The nearest parts of the Oort cloud may therefore begin more than 100 times farther out than Neptune, depending on where the uncertain boundary is drawn. Its remote outskirts could approach a meaningful fraction of the distance to the nearest neighbouring stars. The cloud is not merely another belt beyond the planets. It is a change in scale so severe that the familiar solar system becomes a bright point near the centre. Distance behaves differently here because the Sun no longer dominates the sky in the way we imagine it from Earth. At Neptune, sunlight is weak, but the Sun is still unmistakably the central object. Far into the Oort cloud, it would appear as an intensely bright star rather than a broad glowing disk. Its gravity would still guide an object along an orbit, yet that orbit might take millions of years to complete. Most of the journey would unfold so slowly that motion would be difficult to notice over a human lifetime. An icy body near the farthest part of its path could seem almost motionless against the stars, even though it remained connected to the Sun by gravity. This is one reason direct discovery is so difficult. The object would be faint, cold, small, and moving only gradually across the background sky. A telescope would need to distinguish it from countless distant stars and galaxies, then observe it long enough to recognize that the faint point had shifted. The outer solar system has no objection to being studied. It simply prefers a schedule longer than most research grants. When astronomers speak about the inner edge of the Oort cloud, they are not identifying a physical surface. They are choosing a region where orbital behavior begins to fit a particular model. Closer to the Sun, Neptune and the other giant planets can still reshape the paths of scattered bodies. Farther out, an object may have its closest approach lifted away from the planets by passing stars or galactic gravity, allowing it to remain in a distant orbit for immense periods. The boundary depends on what kind of object is being discussed and which formation model is used. Some estimates place a possible inner reservoir at a few thousand astronomical units. Other definitions begin closer or farther away. There may be no empty gap separating the scattered disk from the inner cloud. Instead, one population may thin gradually as another becomes more important. A body does not cross a line and suddenly become an Oort cloud object. Its classification depends on its entire orbit, the forces that shaped it, and the scientific language chosen to describe that history. The outer edge is even more difficult to define. At some distance, the Sun's grip becomes so weak that the surrounding galaxy can remove objects more easily than the Sun can retain them. But this does not happen at one perfect spherical boundary. An object's stability depends on the shape and orientation of its orbit, the direction of galactic forces, and the history of stellar encounters nearby. Two bodies at similar distances might have very different futures. One could remain bound for billions of years. Another might be nudged onto an escape path during the passage of a star. The cloud's edge may therefore be irregular, changing and slightly compressed or stretched by the solar system's movement through the Milky Way. It is useful to picture the outskirts of a town at night. Streetlights become farther apart, houses give way to open land, and eventually another district begins to exert more influence than the centre you left behind. Yet no single step marks the exact end. The comparison has limits because gravity is not municipal planning, but the fading influence is similar. This enormous scale also means that the Oort cloud cannot be crowded in the way the word cloud suggests. Even if it contains hundreds of billions or perhaps more small bodies, those objects would be spread throughout a volume almost unimaginably larger than the planetary system. A spacecraft moving through the region would probably see no nearby comet at all. The sky could look nearly unchanged for centuries of travel. There would be no glowing haze, no continuous field of ice, and no dramatic moment of arrival. Most objects would remain separated by distances far greater than the spaces between familiar planets. A large total population can coexist with profound local emptiness because the available volume expands so rapidly with distance. This is one of the Oort cloud's quiet contradictions. It may be one of the solar system's greatest collections of small worlds, yet almost every point inside it is simply dark space. The cloud exists statistically through the distribution of orbits rather than as a visible object that an explorer could watch approaching through a window. So the shell drawn around the Sun is best understood as a useful summary, not a finished portrait. Its inner boundary depends on how astronomers separate detached objects from more distant populations. Its outer boundary depends on where galactic forces and passing stars overcome long-term solar control. Its shape may vary with distance, perhaps beginning as a more concentrated or flattened inner region, before becoming more nearly spherical farther out. Its scale is reconstructed from comet orbits and computer models rather than mapped body by body. For now, we can keep one simple image in mind: the planets occupy a small, bright central system, while far beyond them lies a vast architecture of elongated paths, each carrying a dark object slowly around the Sun. But those paths may not all belong to one uniform population. The Oort cloud could contain an inner reserve and a more exposed outer region, shaped by different balances of gravity and preserving different parts of the solar system's history. To understand what may be hiding there, we must now look inside this enormous shell and ask whether it is actually made of layers. The Oort cloud may not be one cloud at all. Beneath the familiar spherical shell drawn around the solar system, astronomers suspect there may be at least two overlapping populations, a more tightly bound inner reservoir and a far more exposed outer cloud. Neither has been directly mapped, and the line between them is not sharp. They are ideas built from orbital calculations, simulations of the young solar system, and the paths of comets that eventually reach us. The inner region is often associated with the name Hill's Cloud, after the astronomer who explored how a dense reserve of distant comets might survive closer to the Sun than the outer population. It may begin thousands of astronomical units away, although its precise extent depends on the model. The outer cloud begins farther out and may continue for tens of thousands of astronomical units. Together, these regions form less of a layered shell than a gradual change in how strongly objects are held, how their orbits are arranged, and how easily the galaxy can disturb them. The inner cloud would remain more tightly connected to the Sun. Its objects may follow elongated paths that are tilted in many directions, but the population might still preserve some memory of the flattened disk from which the solar system formed. Some models predict a broad torus or thickened structure rather than a perfectly spherical swarm. Others produce something more complicated, shaped by the migration of the giant planets and the environment in which the young Sun was born, because these objects remain closer to the Sun than members of the outer cloud. Passing stars and galactic tides affect them less strongly. Their orbits can remain stable for enormous spans of time, protected from the most frequent disturbances yet far beyond the reach of ordinary planetary encounters. This makes the inner cloud a possible deep reserve. Even if the outer population is gradually stripped away, the inner region may continue supplying new bodies outward or inward through slow gravitational changes. It is a quiet storehouse behind another quiet storehouse, which is a remarkably elaborate arrangement for objects that spend almost all their time doing very little that we can see. The outer Oort cloud is expected to be different. At those greater distances, solar gravity still binds the objects, but only weakly. Their orbital periods can stretch across millions of years, and their paths may be oriented almost randomly around the Sun. This broad distribution helps explain why long-period comets can arrive from nearly every direction in the sky. The outer population is often imagined as roughly spherical because external gravitational influences have had time to lift tilt and rearrange the distant ends of cometary orbits. Yet roughly spherical should not be mistaken for perfectly smooth. The cloud may be stretched by the galactic environment, depleted in some directions, and uneven because of ancient stellar encounters. It could contain streams, concentrations, gaps, and remnants of earlier disturbances that no current telescope can resolve. The simple shell in an illustration is therefore similar to drawing a forest as a green circle on a map. It tells us where the forest may be, but not where every tree stands, which areas are dense, or which paths have been opened by storms. The relationship between the two regions may be more important than their names. An object in the inner cloud could slowly be moved outward by a passing star or by the accumulated influence of the galaxy. Once it reaches a more exposed orbit, another disturbance might lower its closest approach to the Sun and send it toward the planetary region. An outer cloud object might instead be pushed entirely away, becoming an interstellar wanderer no longer bound to the Sun. Others may be redirected into the inner reservoir where they remain for billions of years. These populations are therefore not sealed compartments. They exchange material through slow changes in orbital energy and direction. A comet's location at one moment does not fully describe its history. Over the age of the solar system, it may cross the invisible boundaries between dynamical regions many times. The terms inner and outer cloud help scientists organize the problem, but gravity does not pause to update the label as an object moves from one category to another. The inner cloud may also help explain how the solar system continues producing long-period comets after billions of years. The outermost population is vulnerable. Passing stars can remove objects, and galactic forces can gradually reshape the cloud. If the solar system relied only on this exposed shell, its distant comet supply might have diminished more quickly. A denser inner reserve could replenish parts of the outer cloud, or send objects into orbits where later perturbations guide them toward the Sun. Computer simulations often require some form of inner population, although its size and efficiency remain uncertain. We cannot count its members directly. We do not know whether it contains billions, hundreds of billions, or a very different number of objects within particular size ranges. Nor do we know the size of its largest bodies. A few known detached worlds may hint at the beginning of this region, but none provides a complete map. Sedna and similar objects are clues, not boundary markers. Their strange orbits tell us that something shaped the distant solar system. They do not yet tell us exactly what that something was. For now, the most responsible picture is layered but unfinished. Closer in lies a possible inner population more tightly bound, perhaps somewhat flattened and relatively protected from the galaxy. Farther out lies a broader, more nearly spherical cloud, whose objects are easier for passing stars and galactic tides to disturb. Between them is no wall, only a gradual shift in distance stability and orbital orientation. Together, they may contain the hidden record of an early gravitational sorting process that sent countless small bodies away from the region where they formed. The outer cloud shows us how the solar system interacts with the galaxy. The inner cloud may preserve the deeper reserve from which that outer population can be renewed. But neither region explains how the objects reach such extraordinary distances in the first place. To find that answer, we must return to the young solar system, when the giant planets were still rearranging their surroundings, and small icy worlds were being thrown outward along paths that would carry them almost to the stars. The Oort Cloud did not begin at the edge of the solar system. Its story began much closer to the young Sun, in a crowded disk of gas-dust ice, and countless small worlds moving among the growing planets. These early bodies, often called planetesimals, were the leftover building blocks of planetary formation. Some collided and joined larger objects, others shattered. Many simply continued orbiting until they passed near one of the giant planets. Jupiter, Saturn, Uranus, and Neptune were not passive landmarks in this young system. Their gravity continually redirected the smaller bodies around them, changing their speed direction and distance from the Sun. A planetesimal approaching a giant planet could leave the encounter on a wider orbit than before. Another could be thrown inward. A third might gain enough energy to escape the solar system completely. The distant comet reservoir may therefore have been assembled from material that originally belonged to a much brighter and busier region, long before the outer darkness became its home. It is tempting to imagine one dramatic encounter launching a comet directly from the planetary region into the Oort Cloud. The real process was probably less tidy. A small body could experience many gravitational encounters over thousands or millions of years. Each passage near a planet altered the orbit a little or a great deal. The planet itself moved almost imperceptibly in response, because gravity always works in both directions, but the smaller body experienced the larger change. Over time, an orbit that once remained near the giant planets might become stretched into a long ellipse, with one end still returning to the planetary region, and the other extending thousands of astronomical units into space. This is a gravitational exchange rather than a simple push. The moving planet can transfer some of its orbital energy to the smaller object, or take energy away from it depending on the geometry of the encounter. Mission planners use the same principle in a controlled form when spacecraft perform gravity assists. The young solar system used it without a mission plan, a schedule, or any particular concern about where the passengers arrived. The different giant planets did not contribute in exactly the same way. Jupiter's enormous mass made it exceptionally powerful. A body passing near Jupiter could be rapidly redirected or expelled from the solar system altogether. Saturn also produced strong changes. Uranus and Neptune, being less massive and farther from the Sun, could scatter icy bodies outward, more gradually, giving outside forces more time to alter the distant parts of their orbits before the objects returned. The precise balance depends on the model used for the early solar system, including where the planets formed and how their orbits migrated. What matters is that the giant planets acted together as a long-running gravitational sorting system. Some material was incorporated into planets or moons. Some remained in the Kuiper Belt and scattered disk. Some was thrown inward, perhaps contributing to periods of intense impacts among the inner worlds. Much of it escaped into interstellar space, and a smaller fraction may have been placed onto enormous orbits that remained weakly bound to the Sun. This sorting process also helps explain why Oort Cloud objects may not all have formed in the coldest outer parts of the original disk. Some could have originated near the growing giant planets, where temperatures and available materials differed from those farther away. If so, the cloud may preserve bodies from a broad range of birthplaces. Two neighbouring objects in the present cloud could have very different chemical histories, even if both now spend nearly all their time in similar darkness. One may contain a mixture formed near the orbit of an ice giant. Another may have begun closer to Jupiter or Saturn before being scattered outward. Later heating radiation collisions and cometary activity would add further differences. This variety matters because comets are sometimes described as perfectly preserved samples of one single outer region. They are better understood as pieces of a disturbed early disk stored far away after a complicated sequence of gravitational encounters. The archive may be ancient, but its shelves were filled during a planetary rearrangement. The early orbits of the giant planets may themselves have changed during this era. Modern formation models often include planetary migration, in which exchanges of energy and angular momentum with the surrounding disk caused the planets to shift gradually from their original positions. As they moved, their resonances swept through populations of small bodies, destabilizing some orbits and protecting others. Neptune's outward migration helped shape the Kuiper Belt. Interactions among the giant planets and the planetesimal disk could also have increased the number of objects scattered toward distant space. The exact history remains debated, and different models reproduce different parts of the solar system we observe today. We cannot rewind the planets and watch the process directly. Instead, scientists compare simulations with the present arrangement of planetary orbits, resonant Kuiper Belt objects, detached bodies, comets, moons, and other surviving evidence. The Oort Cloud is one of the largest consequences of that early history, yet it is also one of the hardest consequences to measure. There is still a problem. A planet can stretch a small body's orbit until it reaches far into space, but unless something changes the orbit again, that body will eventually return to the region of the giant planets. On its next passage, Jupiter or another planet may scatter it once more, perhaps ejecting it completely. Simply throwing objects outward is therefore not enough to build a stable cloud. Their closest approaches to the Sun must somehow be lifted away from the planetary region, disconnecting them from repeated encounters. This change requires only a gentle influence when the object is already very far away, because the Sun's grip there is weak, and the orbit moves slowly. During the solar system's youth nearby, stars may have supplied that influence. Over longer periods, the gravitational field of the Milky Way could continue the work. The giant planets opened the road outward, but the galaxy may have been what closed the road behind some of the travellers, leaving them preserved in distant orbits instead of allowing them to fall back toward the planets. The giant planets could open a road into distant space, but they could not build the Oort Cloud alone. A small icy body scattered outward by Jupiter-Saturn, Uranus or Neptune would usually remain on an elongated orbit, whose nearest point still crossed the planetary region. However distant it travelled, gravity would eventually carry it back. On the return journey, another encounter with a giant planet might change its path again, or expel it from the solar system entirely. To preserve the object in a remote orbit, something had to raise its closest approach to the Sun, lifting that inner end of the orbit beyond the planet's reach. The required change was not enormous once the object had travelled far enough away. Near the distant end of an orbit, it moved slowly, and solar gravity held it only gently. A weak influence applied there could reshape the entire path. The planets supplied the energy that sent the body outward. The surrounding galaxy may then have adjusted the orbit just enough to prevent it from returning to them. The Milky Way exerts gravity on everything in the solar system, including the Sun, the planets, and the most distant comets. Because all of these objects travel through the galaxy together, the important effect is not a single pull dragging them in one direction. It is the slight difference in galactic gravity across the immense size of a comet's orbit. The Sun experiences one pull, while a body tens of thousands of astronomical units away experiences a subtly different one. This difference is called the galactic tide. It resembles an ocean tide only in the broadest sense. Earth's tides arise because the Moon's gravity is slightly stronger on one side of our planet than on the other. In the Oort Cloud, the gravitational field of the Milky Way varies across a much larger region and over far longer periods. The effect is exceedingly gentle, but a distant comet may remain exposed to it for millions or billions of years. Gravity is patient. It can achieve quite a lot when no one insists on seeing the result by next Tuesday. The galactic tide can gradually alter the orientation of a comet's orbit and change the distance of its closest approach to the Sun. For a body recently thrown outward by the planets, this change may lift the perihelion the nearest point of the orbit beyond the region where Jupiter and Saturn can interfere with it. The comet then becomes dynamically detached from the planetary system. It is still bound to the Sun, but it no longer returns close enough for the giant planets to undo the arrangement. Picture a very long floating rope tied loosely near the Sun. The planets have pulled its far end outward, and a slow current changes the direction of that distant end, while the inner portion is almost unaffected. The comparison is limited because an orbit is not a physical rope, yet it captures why the timing matters. External gravity works most effectively when the comet is far away, moving slowly, and only weakly controlled by the Sun. A tiny alteration there can decide whether the object returns to the planets, remains stored in darkness, or eventually escapes. The young Sun may also have formed in an environment very different from the quiet stellar neighbourhood it occupies today. Stars are generally born in groups within large clouds of gas, and the Sun was probably surrounded by other young stars during its earliest history. Those neighbours may have passed much closer than most stars do now. Their gravity, together with the gravitational field of the remaining cluster gas, could have strongly influenced bodies scattered away from the young planets. Computer simulations show that such an environment can produce a compact inner reservoir by raising cometary perihelia relatively close to the solar system compared with the more distant outer cloud. These early encounters may also help explain objects on detached orbits that are difficult to produce using the known planets alone. But this part of the story remains model-dependent. The Sun's birth cluster dispersed long ago. We do not know its exact size, density, lifetime, or the paths of its individual stars. We are reconstructing a vanished neighborhood from the architecture it may have left behind. As the Sun's original stellar group dissolved, the Oort Cloud continued evolving within the wider Milky Way. The steady galactic tide acted continuously, while passing stars supplied shorter and less predictable disturbances. Most stars remained too distant to transform the cloud dramatically during a single encounter, but their cumulative influence mattered. A particularly close or massive passer could alter many exposed outer orbits, sending some bodies inward, pushing others deeper into the cloud and removing a fraction from the Sun altogether. Over the age of the solar system, repeated perturbations may have helped turn an initially flatter population into a more nearly spherical one. Orbital directions became mixed, and the original plane of the planetary disk grew less obvious in the outer regions. This mixing was not perfect, and different models predict different structures. The outer cloud may contain irregularities, fossil patterns from ancient encounters, or uneven populations that remain invisible to us. A spherical illustration is therefore an average description, not a photograph of a smooth shell. The galaxy played two apparently opposite roles. It helped save some scattered bodies by lifting their orbits away from destructive encounters with the planets, and it continued disturbing those same bodies after they were stored. Without external gravity, many would have returned to Jupiter or escaped before a stable cloud could form. With too much disturbance, the Sun would have lost them anyway. The Oort Cloud emerged from a balanced, strong planetary scattering near the centre, weak solar binding at great distance and gentle but persistent influence from the stellar environment beyond. That balance is still active today. The cloud is not a frozen monument left unchanged since planetary formation. Its members continue to exchange energy, alter direction, drift between inner and outer regions, or leave the solar system entirely. Yet many may retain material assembled during the earliest chapters of planetary history. Having followed the forces that placed them in darkness, we can now look more closely at the bodies themselves and ask what kind of record they have carried through all that time. An object hidden in the Oort Cloud may look like a simple lump of frozen material, but even the word ice conceals an entire chemical landscape. Comet nuclei are generally thought to contain mixtures of frozen volatile substances, rocky grains, fine dust, and carbon-rich material. Water ice is important, but it is not alone. Carbon dioxide, carbon monoxide, methane, ammonia, methanol, and other compounds have been detected in the gases released by different comets, although their relative amounts vary widely. Some of these substances begin escaping at greater distances from the Sun than water does, allowing a comet to become active while it is still far beyond Earth. Beneath the dark surface may be pores, fractures, layers, and pockets containing materials with different histories. The old description of a comet as a dirty snowball is useful only as a first sketch. It captures the mixture of ice and dust, but not the complexity, diversity, or sometimes surprisingly dark appearance of the object itself. The snowball has been stored for billions of years, dropped repeatedly, irradiated, warmed, cracked, and given no particular reason to remain neatly mixed. When an Oort Cloud comet enters the inner solar system, astronomers usually study its composition indirectly. Sunlight warms the nucleus, and frozen substances change directly into gas, carrying dust away with them. This creates the coma surrounding the nucleus and eventually the comet's tails. Telescopes separate the light from this gas into a spectrum revealing chemical fingerprints associated with particular molecules and atoms. Yet the coma is not a transparent inventory label. Some substances are released directly from the nucleus, while others are produced when sunlight breaks larger molecules apart. Dust grains may continue releasing gas after they leave the surface. Different regions of the nucleus can become active as it rotates, and the observed mixture can change as the comet approaches the Sun. Astronomers are therefore reading a moving sunlit sample rather than opening the nucleus and examining every layer. The measurements are real, but their interpretation requires models of heat-gas flow chemistry and surface structure. A comet tells us what it's made of gradually and sometimes with the organizational clarity of a cupboard, packed in complete darkness. Spacecraft have shown how misleading a smooth icy picture can be. ESA's Rosetta mission accompanied Comet 67, a short-period comet rather than a known visitor arriving directly from the distant Oort Cloud. Rosetta found a dark, irregular nucleus with cliffs, pits, fractures, dust-covered terrain, exposed patches of water ice, and a rich variety of gases and organic compounds. NASA's Stardust mission returned particles from Comet Wild 2, another comet that cannot simply stand in for the entire Oort Cloud. Those grains included material that had formed under very different temperature conditions, showing that the young solar system mixed matter across great distances before comets were assembled. These missions do not provide a direct sample of the hidden cloud, and their targets have experienced histories unlike those of many long-period comets. Still, they offer an important warning. A comet is not necessarily a uniform piece of untouched outer ice. It can be a loosely assembled body containing ingredients from several regions later altered by heat radiation impacts and repeated activity. This is why scientists use the word primitive more carefully than pristine. Oort cloud objects may preserve material from the period when the planets were forming, but preservation does not mean that nothing has happened since. Even in deep darkness, energetic particles from space can alter surface chemistry. Radiation can break chemical bonds and create new compounds. Occasional collisions may expose fresh layers or cover them with debris. Slow heating by nearby stars during ancient encounters may have affected especially volatile substances near the surface. Internal heat from radioactive elements would have been limited in small bodies, but larger objects could have experienced more change. Some comets may also have visited the inner solar system before losing surface material during earlier passages and then returning to distant orbits. A dynamically new comet has an orbit suggesting that it has not recently approached the Sun yet. This does not guarantee that every molecule inside it has remained in its original state. The archive is old. The pages have simply been edited by processes far quieter than human hands. Despite those changes, the Oort cloud may preserve information that has vanished from the planets. Earth's crust has been melted, recycled, eroded, and reshaped. The giant planets have active atmospheres and inaccessible interiors. Many small bodies closer to the Sun have been heated or repeatedly collided. A distant comet can retain volatile substances that would not survive for long on a warm planetary surface. The proportions of those substances, the isotopes within them, the minerals carried by their dust, and the structures inside the nucleus can help scientists test models of where the object formed and how material moved through the young planetary disk. No single chemical ratio provides a simple birthplace. Comets display considerable diversity, and later processing can blur the evidence, but populations can reveal patterns. Several comets with related compositions may point toward shared formation conditions, while unusual objects may preserve material from a different region or a different stage of the disk's evolution. Each nucleus is less like one complete history book and more like a surviving fragment whose language must be compared with many others. So the frozen records inside the Oort cloud are probably neither perfectly untouched nor hopelessly erased. They may contain water-rich ice, more volatile frozen gases, mineral grains, carbon-bearing compounds, and complex organic chemistry assembled before Earth became a planet. Some bodies may have formed in neighbouring regions of the original disk. Others may contain matter transported outward from much closer to the young Sun. The scattering that built the cloud mixed these objects into distant orbits, where cold conditions slowed many forms of change without stopping them entirely. Only the rare members sent inward become available for study, and those visitors may not represent the hidden population fairly. We see the comets that gravity selects that survive the journey and that become bright enough to detect. Behind them may remain a far larger variety of dark bodies that never approach the Sun at all. To understand the scale of that unseen archive, we must now leave chemistry behind and confront a peculiar numerical question. How can a region contain an extraordinary number of objects while remaining almost completely empty? The Milky Way does not need to touch an Oort Cloud object to change its path. Its influence is already present, spread across the entire distant reservoir as a weak difference in gravity from one location to another. The Sun and a nearby comet both fall through the galaxy together, so most of the galactic pull is shared and produces no dramatic separation between them. What matters is the tiny part that is not shared. An object far above or below the broad plane of the Milky Way feels a slightly different acceleration from the Sun. The same is true for an object displaced toward or away from the galactic center. Across the compact planetary system, these differences are almost negligible. Across an orbit extending through tens of thousands of astronomical units, they become a slow tidal field. Nothing visibly stretches. No wave sweeps through the cloud. The effect is closer to a nearly silent adjustment in the rules of an orbit repeated for so long that the orbit eventually becomes something new. A distant comet follows two gravitational stories at once. The Sun provides the central attraction that keeps it on an immense ellipse, while the galaxy gently changes the orientation and shape of that ellipse. The galactic tide usually does not give the comet one sudden burst of energy. Instead, it can alter the orbit's angular momentum, changing how closely the comet approaches the Sun, while leaving the overall size of the orbit comparatively similar. The farthest point may remain remote, but the nearest point can drift inward or outward. Picture a long narrow doorway rotating slowly around one fixed hinge. The doorway remains roughly the same length, yet its inner end can sweep across very different parts of the room. An orbit is not rigid like a door, but the comparison captures the important distinction. A small change in direction at the distant end can move the comet's future perihelion by an enormous distance. After millions of years, a path that once avoided every planet may begin carrying its nucleus toward the region of Neptune, Saturn, or Jupiter. The strength of this process depends strongly on distance. In the inner Oort cloud, solar gravity holds objects more tightly, and their orbital periods are shorter, leaving the galactic tide less time to reshape each journey. In the outer cloud, a comet moves slowly through a region where the Sun's control is weaker. There the tidal field can change the perihelion substantially during a single long revolution. Orientation matters as well. Some orbital alignments respond more efficiently to the vertical part of the galactic tide, which arises from the distribution of matter around the Milky Way's disk. Other changes are influenced by the radial tide associated with the galaxy's larger gravitational structure. Real calculations include several components and follow how they interact over time. The result is not a uniform inward rain. Some perihelia decrease, some increase, and many orbits pass through long cycles without ever entering the planetary system. The tide opens possibilities. It does not select a destination with any particular sense of urgency. Astronomers sometimes describe the inner planetary region as containing a kind of loss cone in orbital space. This is not a physical cone standing among the planets. It is the range of trajectories that bring a distant comet close enough for the giant planets to alter it strongly. Once a comet enters this range, Jupiter and Saturn may redirect it, shorten its orbit, send it outward again, or eject it from the solar system. The galactic tide can gradually refill this set of vulnerable trajectories by lowering the perihelia of fresh objects from the cloud. Yet there is a complication. A comet beginning in the more tightly bound inner cloud may need a large change before it can cross the planetary barrier. If its perihelion descends only gradually, the giant planets may remove it before the tide completes the delivery. More distant outer cloud comets can sometimes have their perihelia shifted more quickly, allowing them to pass through that barrier in a different way. This balance between slow injection and planetary removal shapes which parts of the hidden cloud become visible to us. Because the Sun itself travels through the Milky Way, the tidal environment is not perfectly constant across all of cosmic history. The solar system moves around the galactic center and also responds to the distribution of stars gas and dark matter in its neighborhood. Researchers study whether changes in that environment may alter the long-term flow of comets. But the result should not be imagined as a precise galactic clock that sends destruction inward at regular intervals. The cloud has a complex distribution of orbits. Individual comets respond differently, and passing stars add irregular disturbances that can overwhelm a simple repeating pattern. Even the present structure of the reservoir is uncertain. Models can predict statistical tendencies, not a calendar of specific arrivals. What we observe is a filtered record comets whose ancient orbits, tidal evolution, planetary encounters, physical survival, and timing all happen to place them within reach of our telescopes. The Milky Way writes slowly and most of its lines remain unread. The same tide that sends a few objects inward can guide others away from the Sun. It can lift a perihelion back into safety, alter an orbit's inclination, or help prepare a weakly bound comet for eventual escape when another disturbance arrives. Over billions of years, this continuing motion helps keep the Oort Cloud alive as a dynamical population rather than a motionless shell. Its outer members are suspended in a delicate region where the Sun remains their home. But the galaxy is always present in the architecture of the journey. Every long-period comet that becomes visible may therefore carry two histories: the early planetary scattering that sent it outward, and the slow galactic influence that eventually turned part of its orbit inward again. Yet the tide is only the background influence. From time to time, a single neighboring star passes close enough to add a shorter, more concentrated gravitational pull. The galaxy works continuously. A passing star arrives as an event. A passing star does not need to approach the planets to rearrange part of the Oort Cloud. The cloud is so enormous that a star can remain unimaginably far from Earth while crossing close to its outer population. From the inner solar system, the visitor might appear as nothing more than another faint point moving slowly across the sky. Far beyond Neptune, however, its gravity would add a temporary pull to the gentle attraction of the Sun and the broader tide of the Milky Way. The encounter might last thousands of years, brief compared with the orbital periods of distant comets, but far too gradual to resemble a sudden blow. No visible wave would race through the cloud. Most objects would continue along nearly unchanged paths. Yet those lying in favourable locations could receive enough of a gravitational adjustment to alter where their next orbit carried them. A close stellar passage is therefore an event only by cosmic standards, concentrated compared with the constant galactic tide, but still slow enough that many generations could pass before its consequences entered the planetary system. The effect depends on four main features of the encounter: the star's mass, its speed, its closest distance from the Sun, and the direction from which it passes. A more massive star produces a stronger gravitational influence. A slower encounter gives that influence more time to act. A closer passage creates a larger difference between the pull felt by the Sun and the pull felt by a distant comet. Geometry determines which objects are pushed inward, which are lifted outward, and which barely notice. Imagine a broad field of small compass needles arranged around one central lamp. A moving magnet passes along one side of the field. The needles nearest its path respond more strongly, while those far away turn only slightly or not at all. The comparison is imperfect because Oort Cloud bodies are not fixed in place, and the gravitational encounter changes their velocities rather than merely their orientation. Still, it shows why the cloud does not react as one solid object. Each comet experiences the passage from a different position on a different orbit. For some bodies, the star's pull can reduce the distance of their next perihelion, bringing the inner end of the orbit closer to the Sun. A comet that once remained safely beyond the planets may begin a journey toward Neptune, and eventually the region where Jupiter and Saturn can reshape its future. Other objects experience the opposite change. Their perihelia rise, protecting them from the planetary system for another long interval. Some gain enough orbital energy to become only weakly bound, leaving them vulnerable to a later encounter or to the galactic tide. The most exposed members may be removed from the Sun altogether and begin travelling independently through interstellar space. The same stellar passage can therefore produce inward visitors, more distant survivors and escaping wanderers. There is no single front moving through the cloud and no universal direction of travel. Gravity alters a distribution of possibilities. The outcome for each body is written by its exact position and velocity at the moment the neighbouring star passes. Astronomers sometimes discuss a temporary increase in the number of comets entering the inner solar system after a strong perturbation. This is often called a comet shower, but the phrase can sound more dramatic and immediate than the physics requires. It does not imply a bright storm suddenly filling Earth's sky. The disturbed objects begin at different locations and follow orbits with different lengths, so their inward journeys are spread across very long periods. Many never come close to Earth. Some are redirected or ejected by the giant planets before they reach the inner system. Others may fade, fragment, or remain too faint to detect. Even a substantial disturbance produces a statistical enhancement, rather than a predictable sequence of specific arrivals. Researchers can model how a passing star changes the likelihood of comet injection, but they cannot turn that calculation into a precise calendar of future apparitions. The Oort Cloud contains too many unknown objects, and small uncertainties in stellar motion grow when projected across immense spans of time. The effects of passing stars also work together with the galactic tide. A comet may spend millions of years having its orbit slowly prepared by the Milky Way's gravitational field, then receive a more concentrated adjustment during a stellar encounter. In another case, a passing star may move the object into an orientation that allows the tide to lower its perihelion more efficiently later. Simulations indicate that these two influences cannot always be treated as separate mechanisms, whose results are simply added together. Their interaction can deliver comets to observable orbits more effectively than either process acting alone. The inner and outer cloud may respond differently because their members are held with different strengths. Farther objects are easier to disturb but also easier to lose. More tightly bound bodies require a stronger or better aligned encounter before their paths change substantially. Over billions of years, repeated flybys may have removed a significant fraction of the original outer population while continually rearranging what remained. We learn about these encounters by measuring the positions, distances, and velocities of nearby stars, then calculating their motion backward or forward through the galaxy. Precise astrometric surveys have greatly improved this work, but every predicted encounter carries uncertainty. A star's present motion must be measured in 3 dimensions, including its speed toward or away from us. The gravitational field of the Milky Way must be modelled. Tiny uncertainties expand when the trajectory is followed for hundreds of thousands or millions of years. New measurements can therefore revise the estimated time or distance of a passage. The purpose of these calculations is not to announce a distant threat. It is to understand the changing stellar environment through which the solar system travels, and to estimate how that environment shapes its most remote objects. The Sun has never crossed the galaxy alone. It moves among stars whose paths occasionally pass near enough to leave subtle marks on the hidden cloud. After such an encounter, no comet carries a label explaining what happened. One may begin falling toward the Sun along an orbit lasting millions of years. Another may move into the deeper reserve of the inner cloud. A third may escape carrying material from the solar system into the space between stars. By the time an inward traveller develops a visible coma, the star that altered its path may be far away, and the gravitational meeting may have occurred before humans existed. Reconstructing the cause requires working backward through planetary disturbances, galactic tides, measurement uncertainties, and the comet's own activity. Often the answer remains probabilistic, but the range of possible futures is clear. A disturbance in the Oort Cloud does not merely send objects toward us. It opens several quiet roads inward to the planet sideways into a new distant orbit, or outward beyond the Sun's weakening hold. A comet disturbed from the Oort Cloud does not receive one predetermined destination. The same small change in velocity that begins its inward journey can eventually lead to several very different futures. Some objects return to distant storage after passing the Sun. Some are captured into shorter orbits. Some collide with the Sun or a planet, although such outcomes are rare compared with the enormous number of harmless passages through empty space. Others are thrown outward so strongly that they never return. The difference may depend on a single encounter with Jupiter, the exact direction of a jet escaping from the comet's surface, or a slight variation in an orbit accumulated across millions of years. By the time the comet enters the planetary region, the galaxy has already handed it back to the Sun. The giant planets then decide through gravity rather than intention whether the visitor remains a member of the solar system. The first inward passage may carry the comet from deep cold into rapidly increasing sunlight. Far from the Sun, the nucleus remains dark and mostly inactive. As it approaches, highly volatile substances can begin escaping, followed later by water vapor and increasing amounts of dust. The comet brightens, but this activity also changes it. Gas flows through pores and fractures. Jets push unevenly from the rotating surface. Dust settles in some places and leaves others exposed. Weak structures may collapse or separate. A dynamically new comet can therefore enter the inner solar system on an orbit that is ancient, while its visible form changes from week to week. Gravity controls the broad route, but outgassing can produce small deviations that astronomers must include when calculating where the comet came from and where it will go next. Most of these deviations are tiny beside the influence of a planet, yet the comet's future may be balanced so delicately that a tiny push matters. If the comet passes through the planetary region without a close encounter, it may continue around the Sun and begin climbing back toward the Oort Cloud. Its orbit will not be perfectly identical to the one on which it arrived. The combined gravity of the planets produces small alterations even from a distance, while solar heating has changed the nucleus and its activity. The comet may return to an orbit lasting hundreds of thousands or millions of years. It may never become visible to humans again. During the long outward journey, its coma fades, the tail disperses and the nucleus cools until it once more resembles a nearly invisible piece of dark material. The bright comet that crossed our sky was only one brief phase of a much longer orbit. Long after its name has passed from ordinary memory, it may still be moving outward slower each year toward a turning point beyond the reach of present telescopes. A closer encounter with a giant planet can rewrite the orbit much more dramatically. Jupiter is particularly effective because of its mass and location near the region through which many comets pass. Approaching from one direction, a comet may leave the encounter with less orbital energy, becoming more tightly bound to the Sun. Its period can shrink, allowing it to return more frequently. Repeated planetary encounters may eventually place it among shorter period comet populations, although the pathways between dynamical groups are complex and not every captured object remains stable. Approaching from another direction, the comet may gain energy. Its orbit expands, perhaps carrying it into a more distant part of the cloud. With a sufficiently strong change, the orbit can become unbound. The comet then follows a path that will not curve back toward the Sun. In diagrams, the change from an extremely elongated ellipse to an escape trajectory can look almost insignificant. In reality, it separates a future return from permanent departure. An escaping comet does not suddenly leave the solar system at one obvious border. It continues outward through the planetary region beyond the Kuiper Belt, through the heliosphere, and into interstellar space, while the Sun's gravity weakens gradually behind it. Its speed relative to the Sun may be modest, and the journey across the Sun's distant domain can take a very long time. Eventually it becomes another small object travelling between stars. The Milky Way contains material lost from many planetary systems, so interstellar space may be crossed by countless frozen bodies too faint to detect. A few interstellar objects have been observed passing through our own planetary region, but their individual birth systems are unknown. In the same way, comets expelled by Jupiter may one day enter the distant outskirts of another star. Most will pass unnoticed. Planetary systems quietly exchange debris without ever coming close enough for their planets to meet. Other inward travellers do not survive as single objects. A comet can fragment when thermal stress, rapid rotation, internal gas pressure or tidal forces overcome its weak structure. Some fragments continue along related orbits, producing families of objects or streams of dust. Others fade until they become difficult to recover. The disappearance of a comet from observation does not always mean that every piece has been destroyed. It may have become inactive, broken into fragments too faint to track, or moved onto an orbit whose uncertainty expands beyond useful prediction. These physical losses complicate estimates of the Oort Cloud population. The number of visible comets is shaped not only by how often gravity sends them inward, but also by how many remain active and intact long enough to be discovered. The solar system receives messengers from the cloud, but some arrive with their records damaged during delivery. For every comet that enters a telescope catalogue, an enormous number remain on distant orbits. Some are gently redirected without ever approaching the planets. Some move between the inner and outer cloud. Some are stripped away by stellar encounters. Others may continue circling the Sun for nearly its entire remaining lifetime. Their futures form a branching network of gravitational possibilities, rather than a simple cycle of departure and return. A comet visible tonight could be making its first close visit one of several returns or its final passage before escape. We can estimate its history from the orbit and study its material while sunlight makes it active, but much of its earlier journey remains hidden. To learn more, astronomers need wider surveys, more precise orbital measurements, and perhaps a spacecraft waiting for the right visitor. The Oort Cloud itself may remain beyond practical reach, but one of its messengers could bring the distant archive close enough to examine. Exploring the Oort Cloud may begin without sending a spacecraft anywhere near it. The distance is simply too great for an ordinary mission. Voyager 1, one of the fastest human-made objects travelling away from the Sun, has crossed the heliopause, but the heliopause is only a boundary of the solar wind. The main Oort Cloud lies vastly farther away. A probe launched today could require thousands of years merely to reach its more distant regions, and even then it would face another problem. The objects are spread so widely that entering the cloud would not guarantee passing close to anything. A spacecraft might travel through its darkness for centuries without seeing a single nucleus nearby. The practical route is therefore reversed. Rather than carrying instruments outward to the cloud, astronomers wait for gravity to carry one of the cloud's possible members inward. The comet becomes a natural sample return system, although it declines to include a return capsule, a landing guide, or any assurance that it will arrive when the mission budget is ready. Finding these visitors early is essential. A newly discovered long-period comet may still be years from its closest approach to the Sun, but its faintness and slow apparent motion can make it difficult to recognize. Wide-field surveys repeatedly photograph large areas of the sky and compare each image with earlier observations. Stars and distant galaxies remain nearly fixed while asteroids and comets shift position. The Vera C. Rubin Observatory is designed to perform this kind of repeated, wide survey with an exceptionally large digital camera. Its observations can reveal faint moving objects sometimes before they become active enough to grow an obvious coma. Other ground-based surveys contribute different sky coverage, observing schedules and wavelengths. NASA's planned NEO Surveyor mission is primarily designed to find asteroids and comets that approach Earth's orbital neighborhood using infrared light to detect the heat of dark objects. It will not map the Oort Cloud, but discoveries made after distant visitors enter the inner solar system can still enlarge the sample from which astronomers reconstruct the hidden reservoir. Once a comet is found, precision becomes more valuable than spectacle. Observatories measure its position night after night, extending the observed arc of its motion. An orbit based on only a few measurements may change substantially as new data arrive. With a longer arc, astronomers can estimate the comet's original trajectory before recent planetary encounters altered it, and they can project its likely path after it leaves the inner system. The calculations must account for the gravity of the Sun and planets, the shifting location of the observer, and sometimes the small forces created by cometary outgassing. Researchers can then compare the orbit with models of galactic tides and stellar encounters. ESA's Gaia mission completed its observing operations in January 2025, after measuring the positions and motions of roughly 2 billion stars and other objects. Its accumulated data allow astronomers to reconstruct the paths of stars that passed near the solar system in the past, or may approach in the future. These stellar histories do not identify the exact birthplace of every comet, but they help describe the gravitational environment that has continually reshaped the cloud. Light provides another form of exploration. As a comet warms, telescopes can separate its reflected and emitted light into a spectrum. Different gases leave distinct patterns, allowing scientists to identify water-related molecules, carbon-bearing compounds, and other volatile substances escaping from the nucleus. Infrared observations reveal materials that may be difficult to study in visible light. Radio telescopes can detect certain molecules within the expanding coma. Measurements of dust reveal grain sizes, mineral properties, and how particles respond to sunlight. Polarization, brightness changes, and the motion of jets can provide clues about surface texture, rotation, and internal structure. None of these observations gives a complete inventory. The gas around a comet has been altered by sunlight chemical reactions and the physical process of leaving the nucleus. Dust sampled from one active region may not represent material buried deeper inside. Still, combining many techniques allows astronomers to examine an Oort cloud messenger without touching it. The distant archive is read through material temporarily lifted into the light. A spacecraft encounter could bring us closer. ESA's Comet Interceptor is being developed to launch toward the Sun-Earth Lagrange point known as L2, where it can wait for a suitable target discovered after launch, instead of selecting a familiar periodic comet years in advance. The mission is intended to respond to a comparatively fresh visitor, ideally a dynamically new comet approaching the Sun for the first recorded time, although a suitable interstellar object could also become the target. The mission design includes a main spacecraft and two smaller probes that would separate before the flyby. Observing the nucleus from several paths could reveal its shape surrounding gas-dust environment, magnetic interaction, and changing activity in 3 dimensions. The encounter would be brief because matching the comet's speed for a long rendezvous would require far more propulsion. The spacecraft would therefore cross the environment quickly, gathering as much information as possible while protecting its instruments from dust. The mission cannot yet promise which object it will visit. Waiting for an undiscovered target is part of both its scientific value and its uncertainty. Even the closest successful flyby would examine only one traveler. Its composition might be common within the cloud, or it might be unusual. Its orbit could have originated in the outer population, the inner cloud, or a more complicated transitional region. Its surface may have been altered during the journey inward. To understand the reservoir, scientists must compare that detailed encounter with the broader statistical record, thousands of comet orbits, survey detection biases, chemical measurements, stellar motion catalogues, and simulations of planetary formation. One object supplies texture, populations supply structure. The Oort cloud will probably become clearer through accumulation rather than one dramatic discovery. Each newly measured comet narrows some possibilities while opening others. Each survey improves the census. Each mission studies one page carried from the archive, never the whole library. This indirect approach may sound incomplete, but much of astronomy works in the same way. We do not hold a star in a laboratory or place a detector inside a distant galaxy. We study light motion timing, chemistry, and gravitational effects, then test whether one explanation can connect them. The Oort cloud is an unusually quiet example of this method, because the main structure remains almost entirely unseen. Yet its messengers reach us, its orbits can be calculated, and the forces shaping it can be modelled with increasing precision. We may never photograph the entire cloud as a pale sphere around the Sun. Instead, the picture will emerge point by point, a comet discovered early, a stellar passage measured more accurately, a spectrum recorded, a nucleus crossed by a waiting spacecraft. With those fragments gathered, we're ready to return to the original question and separate what is probably hiding there from what the darkness still allows us only to imagine. What is really hiding inside the Oort cloud is not one dramatic secret waiting to be uncovered. There is probably no single lost planet at its centre, no wall of ice surrounding the solar system, and no bright boundary that a future spacecraft could cross and photograph. The clearer scientific answer is quieter. The Oort cloud is thought to be an immense and extremely sparse population of small bodies moving along distant orbits around the Sun. Many are probably mixtures of ice, dust, rock, and carbon-rich material left from the era when the planets were forming. Some may be only a few kilometers across, others could be much larger. They are separated by such enormous distances that even a cloud containing hundreds of billions, or perhaps trillions of objects would still appear almost completely empty. What hides there is not a crowded kingdom of frozen worlds. It is a scattered archive, spread so widely through darkness that we usually become aware of one of its members only after gravity sends it inward. What we know begins with the comets themselves. Long-period comets enter the planetary system from a wide range of directions, following paths that often extend far beyond the region of Neptune and the Kuiper Belt. Their motion can be measured, their orbits can be reconstructed, their gases and dust can be studied when sunlight warms their nuclei. We also know that the giant planets are capable of scattering small bodies onto enormous orbits, and that the Milky Way and passing stars can alter those orbits over very long periods. These are not imaginary mechanisms added to complete a convenient story. They arise from gravity and can be tested with observations, calculations, and simulations. Together they explain how a body formed near the young planets could be thrown outward, detached from further planetary encounters, stored for billions of years, and eventually redirected toward the Sun. The cloud itself has not been photographed, but the physical processes required to create and disturb such a reservoir are well established. The evidence suggests a structure more complicated than the smooth sphere shown in simple diagrams. There may be a more tightly bound inner population, perhaps somewhat flattened or uneven, surrounded by a distant outer cloud whose orbits point in nearly every direction. The inner region may preserve objects that are difficult for ordinary galactic tides to disturb. The outer region may supply many of the long-period comets that become visible from Earth. Ancient stellar encounters may have left irregular patterns within both populations, while billions of years of galactic influence may have removed some objects and rearranged others. The cloud may contain material formed across a broad part of the original planetary disk, not merely in one cold zone at the solar system's edge. Some bodies may carry minerals created closer to the young sun. Others may preserve especially volatile substances that survived in deep cold. The archive is likely mixed, incomplete, and altered, but still ancient enough to remember conditions that the planets themselves have largely erased. What remains unknown occupies a much larger space. We do not know exactly where the cloud begins. We do not know where its outermost stable orbits give way to interstellar space. We cannot confidently count its members or weigh its total mass. We do not know the size of its largest hidden bodies, whether undiscovered dwarf worlds move through its inner reaches, or how many objects may have been captured from the Sun's original stellar neighborhood. We cannot look at one incoming comet and identify the exact point from which it departed. Nor can we assume that the visitors reaching us are representative of everything that remains behind. Gravity selects which objects travel inward. Sunlight selects which become active. Telescopes select which are bright enough and well placed enough to detect. Our knowledge is filtered at every stage. The result is not ignorance, but a map with broad regions drawn confidently and many smaller details left blank. Perhaps the most important discovery is that the Oort Cloud is not separate from the rest of the universe. It formed through the planets, but it was completed by the Sun's stellar surroundings. It remains connected to the Milky Way through a gentle tidal field, and its outer members can be disturbed by stars passing at distances that would leave the planets untouched. Some of its comets return toward the Sun, some remain hidden, some escape and begin travelling between the stars, just as objects from other systems may occasionally pass through our own. The outermost solar system is therefore not a sealed container. It is a slowly exchanging region where the gravity of one star fades into a larger galactic environment. The Sun remains the central anchor, but not the only influence. At this distance, belonging becomes a matter of balance. We began with the image of a comet appearing from darkness. At first it was only a faint moving point carrying no visible sign of the immense reservoir behind it. Then sunlight warmed its surface. Gas expanded. Dust scattered light. A tail grew across the sky, and for a short time an object stored beyond the planets became something human eyes could notice. That comet could not show us the entire Oort Cloud. It could offer only one orbit, one composition, and one complicated history. Yet from many such visitors a larger picture has emerged, a distant population assembled during the solar system's youth, shaped by planets, stars, and the galaxy, and preserved in a region no telescope has yet seen as a whole. Outside your room, the night sky may now look much as it did before this journey began. The stars remain small points. The planets, when visible, still appear close together across the darkness. Nothing marks the direction of the Oort Cloud because it surrounds us on every side, far beyond ordinary sight. Somewhere within it, countless small bodies continue along their slow paths. Most will never enter the inner solar system. They do not need to. Their quiet existence is already part of the answer. The cloud is probably there. Its messengers have reached us. And for now, the greater archive can remain in the dark while the room around you grows still, the questions soften, and you allow yourself to rest.